Quantum Zeno Effect. Imagine a pot of water on a stove. You turn the burner on high, crank it up to the max, and you wait for it to boil. But it never does. The water stays perfectly still, refusing to bubble, refusing to change, for one bizarre reason. You won't stop staring at it. The moment you look away, it would instantly flash into steam. But as long as your gaze is fixed upon it, it remains frozen, trapped in a state of not quite boiling. This sounds like a strange riddle, a paradox designed to twist your mind. And it is. It's a modern twist on a 2,500-year-old puzzle first posed by the Greek philosopher Zeno of Elea. But in the unsettling world of quantum mechanics, this isn't just a philosophical thought experiment. It's a demonstrable physical reality. This is the Quantum Zeno Effect, and it suggests that the simple act of observation doesn't just measure the universe. It can actively prevent it from changing, effectively freezing a tiny slice of reality in time. To understand how this is even remotely possible, we have to first journey into the heart of quantum weirdness, to the experiment that broke classical physics forever, the Double-Slit Experiment. The setup is simple. You have a barrier with two vertical slits in it, and you fire tiny particles like electrons towards it. Behind the barrier is a detector screen that lights up wherever a particle hits. If you cover one slit and fire the electrons, you get what you'd expect: a single band on the screen, a clear pattern of particles piling up behind the open slit. Do the same with the other slit, and you get another single band. Now, what happens if you open both slits? Logically, you'd expect two distinct bands, one for each slit. But that's not what happens. Instead, you get a complex pattern of many bands, an interference pattern. This is the signature of a wave, where peaks and troughs add up or cancel each other out. This means that each individual electron somehow isn't going through one slit or the other. It's going through, behaving as a wave of probability, interacting with itself, and then landing on the screen in a specific spot. This is where it gets truly strange. Physicists, baffled by this, decided to watch. They placed a tiny detector by the slits to see which one each electron actually went through. And the moment they did that, the moment they observed the electron's path, the interference pattern vanished. It collapsed into the two simple bands we originally expected. It was as if the electrons, they were being watched. The very act of measuring, of looking, forced the electron to abandon its ghostly wave-like state of multiple possibilities and snap into a single, definite reality. This is the observer effect, the foundational principle that measurement isn't a passive act in the quantum realm. The observer is a participant. The tool you use to see something inevitably interacts with it, changing the outcome. The Quantum Zeno Effect takes this principle and cranks it up to an unthinkable extreme. If one observation forces a particle to choose a state, what happens if you don't just look once, but continuously? What if you perform a series of incredibly rapid-fire measurements, one after another, without giving the system a moment to breathe? This is where Zeno's paradox re-enters the picture. The original paradox described a race between the swift hero Achilles and a slow tortoise. The tortoise gets a head start. Zeno argued that for Achilles to catch the tortoise, he must first cover half the distance between them. Then he must cover half of the distance, and then half of remaining distance, and so on, ad infinitum. Because there are infinite halves to cross, logically, Achilles can never actually catch the tortoise. We know in our macroscopic world this is false. It's a mathematical trick. But in the quantum world, this logic holds a terrifying power. Consider an unstable radioactive atom. Quantum mechanics says it exists in a superposition, a ghostly blend of its initial undecayed state and its final decayed state. Over time, the probability of finding it in the decayed state increases. Eventually, it's almost certain to have decayed. But what if we measure it? The moment we check, we force it to choose. It's either decayed or it hasn't. Let's say our first measurement finds it hasn't decayed. We've now collapsed its wave function back to 100% undecayed state. The clock of probability has been reset. Now we let it evolve for a tiny fraction of a second. The probability of decay starts to creep up again. But before it can get very far, we measure it again, and again, and again. Each time we look, we find it undecayed and slam it back to its starting point. The system is effectively pinned to its starting line, never getting the chance to evolve towards decay. We have, in essence, become the pot watchers from our original analogy. This isn't just a theory. In 1989, a team led by physicist Wayne Itano at the National Institute of Standards and Technology demonstrated this in a landmark experiment. They took a few thousand beryllium ions and held them in an electromagnetic trap. These ions could exist in two energy states, a stable ground state and a higher unstable energy state. The team would put the ions into the unstable state, from which they would naturally decay back to the ground state over time. The observation was a series of very short ultraviolet laser pulses. Each pulse was a measurement, checking to see if an ion had decayed. The results were astounding. When they applied the measurement pulses infrequently, the ions decayed as expected. But as they increased the frequency of the laser pulses, as they watched the ions more and more closely, the rate of decay plummeted. With very rapid, continuous observation, they could almost completely suppress the natural evolution of the system. They had frozen the atoms in their unstable state, proving that the watched quantum pot truly never boils. The act of looking had literally stopped time for those particles. Reality and consciousness. The fact that we can physically halt the natural progression of a quantum system just by watching it is a conclusion so profound it borders on cosmic horror. It shatters our most fundamental assumption about the universe, that we are merely passive spectators cataloging a reality that exists independently of us. Block 1 established the how, the mechanics of wave function collapse under rapid, repeated measurement. Now, we must confront the terrifying so what. If observation is an active, creative force that can stop time at the quantum level, what does this imply about the nature of time itself, the structure of reality, and the most mysterious entity of all, our own consciousness? This isn't just physics anymore. It's a direct challenge to our perception of existence. Let's start with time. We experience time as a continuous flowing river, carrying us relentlessly from a fixed past into an open future. But the Quantum Zeno Effect offers a radically different and deeply unsettling alternative. It suggests that for a quantum system, change and evolution are things that happen in the gaps, in the moment's observations. Progression is what occurs when the universe isn't being pinned down by a measurement. This leads to a wild philosophical question. Is the universe a film reel that only advances in the dark? Could it be that at the most fundamental level, reality is a sequence of discrete, frozen quantum moments? Perhaps the state of the universe is a static frame, and the passage of time is simply the process of that frame evolving into the next one, a process that can only happen when it's not being measured.
In this view, our continuous perception of a smooth flow of time is an illusion, a high-level summary of an incredibly jittery start and stop process happening at the Planck scale. This inevitably leads us to the most controversial and exciting part of the puzzle: consciousness. The classic Copenhagen interpretation of quantum mechanics, championed by pioneers like Niels Bohr and Werner Heisenberg, famously invoked the role of an observer in collapsing the wave function. For decades, this led to semi-mystical speculation. Does it take a conscious mind to make reality concrete? Does the universe need us to look at it in order to be real? The Quantum Zeno Effect seems to pour gasoline on this fire. If observation can freeze an atom, does that mean our mind is directly entangled with the physical state of the universe? It's a tantalizing egocentric idea that the cosmos somehow requires a conscious audience to perform. However, modern physics has a more sober and perhaps even more profound answer: decoherence. The observer doesn't have to be a human with a PhD. It doesn't even have to be a living thing. An observation or measurement in the modern view is any interaction a quantum system has with its wider environment that reveals its state. A single photon bouncing off an electron is a measurement. A stray air molecule bumping into it is a measurement. This is the reason you can't freeze your friend by staring at them, or stop a car by taking a video of it. Macroscopic objects are unimaginably complex. A cat is not an isolated quantum system. It's being measured trillions upon trillions of times every nanosecond by the air, the light, the floor, and its own internal vibrating atoms. It is in a state of constant chaotic decoherence. Its wave function, if it ever had a macroscopic one, was collapsed before the universe was a second old. The Zeno effect is a fragile, delicate flower that can only bloom in the pristine, isolated vacuum of a quantum laboratory. Yet, this doesn't diminish its importance. In fact, it's becoming a crucial tool. In the race to build functional quantum computers, decoherence is the ultimate villain. Quantum bits, or qubits, which derive their power from existing in a superposition of states, are incredibly fragile. The slightest interaction with their environment can destroy the delicate quantum information they hold. The Zeno effect, once a philosophical curiosity, is now being weaponized as a shield. By carefully and continuously measuring a qubit in a specific way, scientists can use the effect to lock it into a desired state, protecting it from environmental noise and preventing it from decohering. The very paradox that freezes time is being used to build the future of computation. Interestingly, there's even an anti-Zeno effect, where in some specific circumstances, frequent observation can actually speed up a system's decay, adding another layer of bizarre complexity. So, where does this leave us? We stand at a strange crossroads. On one hand, the grand dream of our consciousness shaping reality is tempered by the mechanics of environmental decoherence. But on the other, the fundamental truth remains unshakable. Reality at its base is not a solid pre-written book. It's a shimmering cloud of probabilities, a ghost of potential that only solidifies into the definite now through the act of interaction. We are not just reading the story of the universe. The very act of reading, of measuring, of observing, of interacting is what forces the ink to dry on the page. We are not passive spectators, we are co-authors of the present moment. The universe doesn't just wait for you to see it. In a way, it waits for you. The most profound changes, the very unfolding of time, might just occur in the moments when you're not looking.